Welcome. Today we're going to start a new unit that involves systems of equations. The first lesson is going to be talking about systems of equations that involve a linear equation, but to change it up a little bit from what you explored in Algebra 1, we're going to mix the linear equation with a quadratic equation. And there are different ways that we can solve these. We'll explore several of them. Let's start by looking at the number of solutions that you can have, the types of systems that you can have. So when we are talking about linear equations, this is a review of what we learned in Algebra 1, you can have two intersecting lines that have one solution, remembering that the solution is the ordered pair that represents the spot on a graph where the lines intersect, or if you're thinking about solutions as x and y values, then those x and y values are such that they make both systems of equations true statements. You can have parallel lines, in which case they never cross. They have the same slope, different y-intercepts, and therefore there are no solutions. And lastly, you can have coinciding lines, and coinciding lines are essentially the same line represented with perhaps different coefficients before y. They have the same slope and the same y-intercept. I didn't mention it, but intersecting lines will have different slopes and different y-intercepts. Okay, so that's what we already know. That's our prior learning. Let's take a moment and look at the steps that we need in order to solve a system of equations using substitution. And remembering that in this lesson, one of our equations will be a quadratic equation. So the first thing we're going to do in substitution is we solve one of the equations for one of the variables. Then we substitute that into the second equation. We solve for the remaining variable. Once we have that remaining variable, then we can substitute it into either the original equation, either of the original equations, to find the original variable we solved for, and then we write our solution as an ordered pair. Seems pretty cyclical, I'm not going to lie, but I think we can master this. So let's look at an example that we can do together. All right, so let's look at example 1. We're going to follow the steps as they're listed up above. Step number 1 being to solve one of my equations for a variable. Try to remember that if you can find a variable that has no coefficient in front of it, it has a coefficient. That coefficient is 1. But in this particular case, solving for y will be easier than perhaps solving for one of the other variable coefficient combinations, just because we are not going to end up with fractions. We're not going to have to do any division. It's a pretty easy win. If I look at this example 2, in this particular case, I would solve for x because x has a leading coefficient of 1, and I can subtract 2y very easily, and I don't have any fractional parts, and I don't have any complicated division that I have to do. Not that division's complicated, but just in case. The easier it is, the fewer mistakes that I'm going to make. All right, I'm going to look at example 1. Example 1, I'm going to start with the second equation. I'm going to start with this one, and I'm going to solve for y. So I starts off with negative 3x plus, and I'm going to make this a different color just so we can see. It matches the color up above in the instructions. Negative 3x plus y equals 15. And if we solve for y, that gives me 3x plus 15 equals y. So now I have isolated one of my variables. I'm going to use the other equation, the one that I did not use, which is this one up here. I'm going to use that one to substitute this y value into. So step number 2 is to take the other equation, slippery paper, and I am going to substitute the value of y into my y variable. So instead of using a y here, I'm going to use 3x plus 15. I'm going to protect him in parentheses. Everything else is written exactly as it originally was. And now if you notice, I have no y variable. All my variables are the same. So I can solve for x. First, I'm going to distribute. I end up with 2x plus 9x plus 45 equals 1. Combine like terms, and I would get 11x. Subtract 45 from both sides. And then if I divide by 11, I end up with a new value for x equals -4. And I made that a different color so we can see when it's substituted. Okay, step number 3 says substitute your answer, x equals -4, into either of my original equations. Not sure why, but I chose to substitute it into the first one. Clearly, it doesn't matter. Remember, I don't know the value of y yet. I know the value of y in terms of x, but I don't know its actual value. But I do know x's value. So I can substitute that in here. And now I only have one variable. Everything else I write exactly the same. This is -8 plus 3y. I add 8 to both sides. I end up with 3y equals 9. So I finally conclude, I'm going to go back to y equals, divide by 3, y equals 3. Step number 4 says write out, you can't see that. Step number 4 says write my solutions as an ordered pair. So I'm going to say that my solution, the place where, and I lied, I said one of these was going to be quadratic. It is definitely not quadratic. So this page is strictly review. My apologies. Probably led you to think something exciting was going to happen. My x value we discovered was -4. My y value is 3. So this is the ordered pair that represents the place on a coordinate plane where these two lines intersect. It also represents an x and y value that when substituted into both of these equations creates true statements. And you can check that answer. I can substitute in my x value and my y value and ask myself, does that equal 1? This was 3. And it should, because that's what we use down here. This is -8 plus 9. Is that equal to 1? And yes, it is. I can check by substituting into my next equation as well. And I'm checking. So this is my y value is 3. My x value is -4. Negative times a negative is positive. Is 12 plus 3 equal to 15? Yes, it is. So now I've verified that my answer is correct. There's really no excuse to get these wrong other than I just didn't bother to check. All right, I'm going to ask you to pause the video, try example 2 on your own, and then check back to see what your solution was. All right, hopefully you came up with a solution of 6, 7, where x has a value of 6 and y has a value of 7. You can step through and see how this was solved. Pause your video if you need to check individual steps. As I said, I started by solving for x because that was going to be sort of the low-hanging fruit and the easiest variable to solve for initially. Let's move on. All right, let's look at a couple of linear examples before we move on to the more interesting stuff. I find that most of my students prefer solving a system of equations using elimination. It is often an easier method. There are a few isolated cases where it's a little more work to do it with elimination. I find that a lot of times I solve something with elimination, and if I am not getting a correct answer, I can use substitution as a different method to verify my steps. The steps being to arrange your equations so that like terms are stacked. That's my term for it. But I want my x's over my x's, my y's over my y's, equal over equal, constant over constant, or any order as long as as there's consistency. So notice here, the x's are lined up, y's are lined up, my equality symbol, and then my constants. In this one, I could choose to move the x to the other side if I wanted to, or I could move this x over to the left so that it mimicked the first equation. Either will work. Sometimes I will add or subtract the two equations that I have stacked, but nothing will be eliminated. In that case, I need to multiply one or both, perhaps, of the equations by some constant so that the coefficient in front of my variables are the same, or at least the same numeric value. They can have different signs, so that when I add or subtract the equations, that variable is eliminated. Once I've eliminated one variable, I'm going to use the steps from the previous page to substitute into either equation to solve for the remaining variable. And then I'm going to write my solution as an ordered pair. Let's try this first example, shall we? All right, step number one is going to be rearranging, easy for me to say, rearranging this one of these equations. And I'm choosing to rearrange this one. What is up with my pen? Rearrange. There we go. Sorry, that looks a little messy. So I'm going to rearrange this by adding x to both sides. And now I have, I can stack my equations. So step number one is to rearrange and stack my equations. I like the 3x minus y equals 4. And if I've added x to both sides here, then I have x plus y equals 8. And I have stacked equations, so I'm ready to eliminate. In order for something to be eliminated, the coefficient in front of the variable needs to match in the two equations. So in this case, I will not be able to easily eliminate the x values, but I will be able to eliminate the y values, both having the coefficient of 1. If I add -1 and +1, that variable will be eliminated. So I'm going to add these two equations. If the signs had been the same, I would have subtracted the two equations. All right, so when I add these, I'm going to add 3x plus 3x plus 3x gives me 4x. And then I notice that these two variables cancel out. And finally, I can say 4 plus 8 is 12. Divide both sides by 4. I get x equals 3. So now I have the value of one of my variables. I can now substitute x equals 3 into either of the equations to find my actual solution. I'm going to substitute it into this second equation. Online, if you check the notes, I substituted it into the first equation. So this is just a way to do something a little different. This was step 1. I did not have to do step 2. This is step 3. So step 4 would be to substitute my answer. I'm going to do, I'll use blue, y. And that is going to be equal to 8 minus my x value. And we've shown that the x value was identified here. So I can substitute that in for the variable, and I get that y is equal to 5. And that was pretty trivial, folks. That was not a super complicated process. Number 5 is to write my solution, and I'm going to abbreviate that. My solution is that x is equal to 3, my y value is equal to 5. That represents the ordered pair where the two lines cross. The ordered pair, the x and y values that make both of these equations true statements. And again, we can check our solution by substituting back into either of the equations to make sure they're true statements. 3 times 3 is 9. 9 minus 5 is 4. So it does work. Pause the video, try number 4, and then come back to check your answers. All right, as I said before, there was no common coefficient in these two equations. They were already neatly stacked, so that's a blessing. But because there was no common coefficient, I needed to manipulate the equations so that either they both had the same x coefficient or they both had the same y coefficient. I could have chosen to change both equations such that they had 12x for the coefficient. That would have required me multiplying the top equation by 4, the bottom equation by 3. The more steps I take, the more likely I am to make a mistake, so I chose not to do that. Instead, I noticed that if I multiplied the top equation by 2, then my y values would match. They would have the same coefficient. So that's what I did. And then down here, I, for some reason, added them. Oh, I multiplied by -2. There we go. So when I multiplied by -2, that changed the sign of my equation. Folks, I'm not sure this is right. Give me a moment. I will check. Yeah. So turns out I just had the signs of these two equations incorrect, but all the rest of them were fine for reasons I don't fully understand. I do get a solution of 1,4. My apologies for that mistake. I can substitute it back into either of my original equations to check and make sure. 4 times 1 is 4. 2 times 4 is 8. 4 plus 8 is 12. So it definitely works for this example. All right, after that short segue, let's try something new. All right, finally, as promised, we are going to look at systems of linear and quadratic equations. Let's look at this first one. The first thing I notice is my top equation is quadratic. My second equation is linear. I'm going to focus on the linear equation first. I just need to extract from it some good information. The first thing I notice is that this equation is in slope-intercept form, which is fantastic because we are going to look for solutions by graphing. And graphing is always easier if my equation starts in y equals mx plus b. I'm going to write my linear equation. Here, let me just identify it here. Ooh, linear. So my linear equation is y equals, and I'm going to make this a 1 because there is a 1 in front of this lovely x that math people are too lazy to write. And my b value is 2. So I can identify that b is equal to 2. That is my y-intercept. My slope is 1. The groovy things to know to graph this line. I am going to grab a straight edge or something that mimics a straight edge. I'm going to start my line at the y-intercept, which is b equals 2. Y-intercept is the value of y when x equals 0. I'm going to use a slope of 1, up 1 over 1, up 1 over 1. And you could do this ad nauseum. I like to get a few points on there, and then I'm going to connect my points, hopefully with some decency here. Might be off by a smidge, not going to stress. The important points are there. Okay, so that's my equation, y equals x plus 2. I have it there. Now I need to graph my quadratic equation so that I can see where, if, and where these lines, these functions intersect. The first one's not a line. Okay, so to find some points and to graph my quadratic, I am going to make a table. Let the calculator make it for you if you feel you need to. I'm going to do some pretty standard points. I have already done this, so I'm not going to bore you with extracting the details. Okay. I cheated and I went ahead and did a sketch of my graph. It's not 100% accurate, but you get the idea. In the interest of time, I thought that best. So what I notice is that this linear function intersects my quadratic in 2 different places. It intersects, had I drawn it correctly, it intersects here at -2, 0. And I can check that just by substituting into my linear equation. -2 plus 2 will give me 0, so that is definitely a true statement for both equations. And then again, my line intersects my quadratic function at 2, 4. So those are my 2 solutions. Sorry, there's lots of lots of things going on here. These are solutions. So what I see is that in this particular case, there are two solutions, and I would want to list those out. Those are -2, 0, and 2, 4. Those are my two solutions. The strategies are the same for the remaining two examples. I notice initially here that x equals 3 is a vertical line. Notice there's no y here. That means it's a vertical line, no y, no slope. So I'm going to draw that vertical line and see the intersection here. This top equation is quadratic and it's in vertex form. So I can identify the vertex as being -2, -1 if I wanted to, but I can also just put this in a calculator and make a table and graph my points. Try that now on your own, those examples, and then let's look and see how you did. All right, I'm cheating and showing you the notes that I have posted online. As I said, this second linear equation is a vertical line, so I went ahead and drew that vertical line through the point x equals 3. And then, as I said, I made a table for my quadratic function, and I sketched it out. And when I did so, I noticed that the vertical line intersects my parabola in exactly one place, and that will obviously be when the quadratic equation has an x value of 3, because that's the only x value I could have. And so in this particular case, my system of equations has one solution, and that solution is 3, 1. Another situation that might occur is when my parabola and my linear function actually never intersect. And that is possible because, if you remember, a parabola changes directions. So there's a whole world, an infinite number of values that parabola will never intersect. So in this particular case, I graphed my line, I graphed my quadratic parabola, my quadratic function in the form of a parabola. I used a table to do that, and I noticed that there were 0 solutions because those two functions will never cross. Therefore, there is no value of x and y, which makes both of those equations true statements. All right, so unfortunately, as easy as it was to solve that system using graphing, graphing doesn't always work, so we need another method. And this is the method that we're going to suggest. It's a little bit more detailed. You might not like it quite as much, but it is very attainable. So what we're going to do is we're going to solve a system of linear and quadratic equations. And the first thing we're going to do is solve each equation for y. We're going to set the equations equal to each other using substitution. We're going to solve the equation that we come up with. And then we're going to substitute our solutions into either the original equation and either of the original equations, and then we're going to solve for the remaining variable. We're going to write our solution as an ordered pair. So that is a familiar set of steps. It's very similar to using substitution for linear equations, but it will look a little bit different. Let's try doing an example together. All right, bear with me because you know I'm a little bit slow. The first thing I'm going to do is I'm going to solve this first equation for y. I notice my second equation is already done, so I'm going to try to get this variable by itself. And to do that, I'm going to go ahead and write it down. Step 1 is x squared minus 6, la, 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 la. I'm going to subtract x from both sides so that I have y by itself, and I'm left with x squared minus x minus 6 equals y. So now I have that variable all by itself. I took it down here. Yes, and now I'm going to substitute this y value in for this one. And when I do that, I continue. This is step 2. I've got x squared minus x minus 6. But instead of writing a y value, I'm going to take this and put it in. I guess I drew too many arrows here. I'm going to put it in here. So I'm going to use 2x minus 2 instead of the y value. All right, so now I notice I only have one variable, so I can solve for x. It is going to be quadratic, so that means I am going to have to do a little factoring. I subtract 2x from both sides, I end up with negative 3x. I add 2 to both sides, I end up with negative 4, and that equals 0. Step 3 is to solve this equation. I'll skip it. So if I solve this equation, x squared minus 3x minus 4, I'm looking for factors of negative 4 that add up to negative 3. I am going to suggest for expediency that this is going to be x minus 4 times x plus 1. And when I solve for each of my x terms, I end up with x equals 4 and x equals negative 1. So that is solving my equation. Now I can substitute both of these x values into my linear function to determine what the y values could be. And remember, because I have two x's, I can have two y values. So I'm going to annoy you by using color here and just write this equation twice, because I'm going to have to do that substitution step twice, once for each variable. So in the first one, I'm going to take x equals 4 and I'm going to shove it down in here. And I'm taking up way too much space, my apologies. 2 minus 2, I end up with y equals 6. I need to do that again in a second version using the second x value, which in this case was negative 1. So I end up with y equals 2 times negative 1 minus 2, and that comes to y equals negative 4. So my solution, which in our steps is step number 5, my solution is going to be, when x equals 4, the y value is 6. And because I have two solutions, I'm going to expedite this a wee bit. When x equals negative 1, the associated y value is going to be negative 4. I can check these solutions by substituting them into both equations to verify that they make true statements. All right, why don't you pause the video, try number 6 on your own, and then come back to see how you did. All right, I hope you noticed that in example 6, much like in the middle example on the previous page, this is a vertical line. So I know that a vertical line crossing a quadratic function will have one intersection. I actually love this problem because there's not a whole lot of work that needs to be done. There is no y value. I have x already isolated, so I can substitute it directly into that quadratic function and I can solve for y. My single solution has to involve an ordered pair where x equals negative 2, and when x is equal to negative 2, my parabola will intersect the line at negative 4.